GenAI and MLOps Part 29. This episode has 5 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Explain model serving architectures. Here's a strong way to approach it. Model serving architecture refers to the design and infrastructure used to deploy, manage, and deliver machine learning model predictions in production environments. It defines how inference requests are received, processed, scaled, monitored, and returned to applications or users. The goal of model serving architecture is to provide reliable, scalable, low latency, and efficient prediction services. Common model serving architectures. 1. Real-time or online serving predictions are generated instantly for incoming requests used in chatbots, fraud detection, recommendations, and APIs. Flow. Client API Gateway Model Server Prediction Response. 2. Batch serving predictions are generated in bulk at scheduled intervals used for analytics, reporting, and large-scale scoring jobs. 3. Streaming inference continuous prediction on streaming data in near real-time used in IoT, monitoring, and event-driven systems. 4. Edge serving models are deployed directly on edge devices for local inference used in mobile apps, smart cameras, and autonomous systems. Core components of serving architecture: load balancer API Gateway Model Server feature store monitoring and logging systems, auto-scaling infrastructure, GPU or TPU acceleration deployment patterns. 1. Single model serving. 2. Multi-model serving. 3. Canary deployment. 4. Blue-green deployment. 5. Champion Challenger deployment. Popular model serving tools: TensorFlow serving, TorchServe, Kserve, Seldon, CoreServe, ONNX. Runtime infrastructure technologies: Docker, Kubernetes, Apache, Kafka, Ginx. From an MLOps perspective, model serving architecture is critical for ensuring scalable deployment, low latency inference, observability, fault tolerance, and continuous delivery of ML models in production systems. Nice. Let's continue. Question 2. What is asynchronous inference? Here's a strong way to approach it. Asynchronous inference is a model-serving approach where prediction requests are submitted to a machine learning system and processed in the background without requiring the client to wait immediately for the response. Instead of returning predictions instantly like synchronous inference, the system acknowledges the request first and delivers the result later once processing is completed. This approach is commonly used for large, slow, or resource-intensive inference workloads. How asynchronous inference works. 1. Client sends inference request. 2. Request is placed into a queue or message broker. 3. Worker nodes process the request asynchronously. 4. Result is stored or returned later through callback, polling, or notification. Common use cases: large language models, LLMs, video processing, batch image analysis, document AI, long-running deep learning tasks, high-volume enterprise workloads. Benefits: better scalability, improved system throughput, reduced request timeout issues, efficient resource utilization, supports long-running inference jobs. Challenges: increased architectural complexity, result tracking and synchronization, queue management, delayed response handling. Common components: message queues, worker services, auto-scaling infrastructure, storage systems, notification services. Popular technologies: Apache, Kafka, RabbitMQ, RayServe, Kserve, Celery. Kubernetes. Difference between synchronous and asynchronous inference. Synchronous inference: client waits for immediate prediction response. Asynchronous inference: client submits request and receives result later. From an MLOps perspective, asynchronous inference is important for handling scalable, distributed, and compute-intensive AI workloads efficiently in production environments. Great. Moving on. Question 3. Explain streaming inference. Here's a strong way to approach it. Streaming inference is a machine learning inference approach where predictions are generated continuously on real-time data streams as data arrives. Instead of processing data in batches, it is used in systems that require immediate insights and low-latency decision-making. How streaming inference works. 1. Data continuously flows from sources like sensors, logs, transactions, or user events. 2. Streaming platforms ingest the data in real time. 3. ML models process incoming events instantly. 4. Predictions or actions are generated continuously. Common use cases: fraud detection, recommendation systems, IoT monitoring, predictive maintenance, real-time analytics, autonomous vehicles, stock market analysis. Key characteristics: real-time, Processing, low latency inference, continuous event handling, high scalability, event-driven architecture, components in streaming inference architecture, data producers, message brokers or streaming platforms, stream processing engines, model serving layer, monitoring and alerting systems, popular technologies, Apache Kafka, Apache Flink, Spark, streaming, Kserve, TensorFlow, serving, Ray-serve, benefits, immediate predictions and actions, faster business response, better customer experience, real-time anomaly detection, continuous operational intelligence, challenges, high infrastructure complexity, scalability management, real-time monitoring requirements, fault tolerance and recovery handling, handling data spikes and ordering issues from an MLOps perspective. Streaming inference is essential for building scalable, low latency, and event-driven AI systems capable of processing real-time production workloads continuously. Alright, next question. Question 4. What is feature parity? Here's a strong way to approach it. Feature parity in machine learning refers to maintaining consistency between the features used during model training and the features used during inference or production serving. It ensures that the same feature engineering logic, transformations, calculations, and data definitions are applied across both training and serving environments. The main goal of feature parity is to prevent inconsistencies that can lead to inaccurate predictions and training serving skew. Example: if a feature like customer age is normalized during training but not normalized during inference, the model may produce incorrect predictions. Feature parity ensures both environments process the feature identically. Key areas of feature parity: feature transformations, encoding, logic, scaling and normalization, missing value handling, aggregation rules, feature version consistency. Why feature parity is important: prevents training serving skew, improves prediction reliability, ensures reproducibility, simplifies debugging, maintains production model accuracy. Common challenges: separate training and inference pipelines, manual feature engineering differences, version mismatches, real-time versus batch feature inconsistencies. Best practices: use shared feature pipelines, implement centralized feature stores, automate feature validation, apply version control for features, use CI or CD for feature deployment. Popular tools: Feast, TensorFlow, Extended MLflow, Kubeflow. From an MLOps perspective, feature parity is critical for maintaining consistent, trustworthy, and production-ready machine learning systems. Let's keep going. Question 5. Explain data contracts. Here's a strong way to approach it. Data contracts are formal agreements that define the structure, format, quality, schema, and expectations of data exchanged between data producers and data consumers in a system. In ML and data engineering environments, data contracts help ensure that upstream data changes do not break downstream pipelines, analytics, or machine learning models. A data contract typically defines schema and field names, data types required and optional fields, data quality rules, validation constraints, data ownership and SLAs. Example: a customer data contract may specify customer ID must be integer, email cannot be null, sign update must follow ISO date format. If upstream systems violate these rules, automated validation can block bad data from entering ML pipelines. Why data contracts are important: prevent pipeline failures, improve data reliability, reduce schema breaking changes, ensure feature consistency, support governance and compliance, improve collaboration between teams. Data contracts in MLOps. In ML systems, data contracts help maintain feature parity, consistent training data, reliable inference pipelines, stable model performance, better monitoring and observability. Common components: 1. Schema validation. 2. Data quality checks. 3. Versioning. 4. Ownership definitions. 5. Change management policies. Popular tools and technologies: Apache Avro, Protobuf. Great expectations: Apache Kafka, Schema Registry, OpenAPI. From an MLOps and data engineering perspective, data contracts are essential for building scalable, reliable, and maintainable data and ML pipelines across distributed systems. On to the next one. That wraps up this episode. Nice work practicing, and see you in the next one.